Okay, now that I've shared with you, but not recorded for posterity stuff about my colonoscopy. Okay, so today I finish a story about population coding. So if you recall, population coding is all about storing information, storing data like numbers and vectors in the collective activity of a population of neurons. There's evidence that that's what your brain does, that you have different levels of memory. You've got long-term memory, like you can remember your childhood address sometimes, your parents' names, stuff like that, or how to ride a bike, whatever. That's like in the connections in your cortex. Those are stored there. That's like backprop changing connection weights. You have another type of memory in your hippocampus that can sort of update the connection weights temporarily for like a day or two, so you can remember what you wore yesterday or what you had for breakfast today. You didn't sit there thinking like, okay, I want to remember I'm wearing my jeans today so that tomorrow I can be asked that jeans. You have to repeat it to yourself, right? No, you just remember, right? It's just automatically sort of stored. That's called long-term memory. No, short-term memory. Then you have working memory. Working memory is the type of memory where you can store someone's phone number or a number. If I say 8953274, you have to 8593274, 8593274, you have to keep repeating it, right? You have to like keep that, those neurons have to keep firing in that pattern, because as soon as you get distracted, it's gone. What was the number? Smart ass, yeah, okay. Some people have better memories than others. So your working memory is basically, it's based on the activity of a population of neurons, right? If you've ever seen the movie Memento, it's about a guy, and this is a real phenomenon, a guy whose hippocampus is damaged, and that's the part of your brain that does short-term memory, like remembering what you had for breakfast today. So he only has memory and working memory. So within a scene, he knows what's going on, but as soon as there's a break of his attention, it's like he was never there. It's a really fascinating movie, and it's really quite realistic, I've been told. So as soon as you get distracted, now if I asked you the number, what's that number? Maybe some of you remember it, but probably most of you don't. I certainly don't. Working memory. It's because you've used those neurons to encode something else, so they no longer encode that piece of information. That's what we're doing here, encoding information in the collective activity of a population of neurons, working memory. So basically, you got some value. So now this X node on the left here, I'm drawing it like it's a neuron, but really it's more like a piece of data. Maybe I should in the future draw it a different shape. It's like a number that's sort of like a mathematical symbol that we want to encode. These circles in the middle now, those are neurons. Okay, so we're taking some number and we're encoding them. Now there are encoding weights and biases, so this number will get turned into neural activities. Now to decode that value, we imagine again that there's this other number that's being decoded out of it. And again, this isn't really necessarily a neuron, it's more like our conceptual decoding. That's why it's in gray. And we have decoding weights. And I outlined a method for you to, even though the encoding weights and biases are random, you can still decode. You can still decode the number that was encoded in that population by computing decoding weights. So it turns into this least squares problem. It's a linear least squares problem. Linear because it's optimal linear decoding. Okay, so All right, I won't go any longer than that. So in addition, you can encode vectors and decode vectors. So you won't be surprised to hear that the higher dimensional vector you want to encode, the more neurons you're going to want to have in your hidden layer, in your population, to encode it accurately, because they're going to interfere with each other somewhat, right? And then you can decode both of those numbers. You just need a different set of decoders for each. But it's the same formula for both of those. Okay, so then I got down here. How do you solve this least squares problem? So if you've started the assignment 7, you will be tasked with solving a least squares problem. Now you can try to get it to solve this, the normal equations, but there's a pretty good chance you'll run into problems because this H transpose H is often either singular or very close to singular. So it's really not invertible. Instead, we use a singular value decomposition to solve a nearby reduced system. And so the answer that you get is not exactly an answer to the original normal equations. It doesn't matter though, because things are just approximate anyway. Okay, so I was in the process of, how many people here have heard of the SVD before? Maybe not studied it, but heard of it. Okay, so maybe a little more than half. It's extremely useful. Extremely, it's like one of the top 10 algorithms of all time. So basically it splits up your matrix into 3 pieces. The middle one is a diagonal matrix, and the other 2 are what you call unitary or orthogonal matrices. So they have this nice property that the transpose is the inverse of them, essentially, insofar as they're not square necessarily, but U transpose times U, for example, equals I. So on the diagonal of that singular matrix in the middle, it puts them all in order. And those singular values, they correspond to the columns of U and the rows of V transpose. And it's basically like a principal component analysis. In fact, it is exactly principal component analysis, and sorts out explains or models the variance in your matrix in order of descending importance, right? So the first column of U, the first row of V transpose, and that first singular value is the most significant, statistically the most significant one dimension in your data. If you include the first 2 singular values, therefore the first 2 columns of U, first 2 rows of V transpose, that is the 2-dimensional subspace that covers the most variance in your input. So anyway, if H transpose H is singular, that means at some point you reach zeros down here, which means some dimensions have nothing in them. So we can just lop those off, turns out. Just cut them off. And so over here, we decide how many singular values we want to keep, and then we cut everything else off. And then it'll be a corresponding bunch of columns of U that we get rid of, and some corresponding columns of V transpose. So let me use lowercase for these. Whoops, not Tim, trim. Okay, and you'll get a matrix the same size, but it's not exactly the same as the original H matrix. It's going to be the closest lower rank matrix that has a rank of however many singular values you kept. Right? If you kept 18 singular values, then this is a rank 18 matrix, which means only 18 of its columns are linearly independent. So this gives you a low rank approximation to H. But the nice thing is H tilde transpose H is non-singular. Which means it's invertible. Which means now we can use that to solve the least squares problem. Okay, so I'll just go quickly through this. Well, maybe I'll just leave it as an exercise to the reader. If I use this decomposition here, U sigma V transpose is H tilde, and I need to solve H tilde transpose H tilde D equals H tilde transpose X. Those are the normal equations, but I've replaced H, the actual coefficient matrix, with H tilde, this low rank approximation. So if you substitute U sigma V transpose in for all the H tildes and reduce it, you can reduce it a lot because you get a lot of things like U transpose times U inside. Well, that's just identity matrix, right? That disappears. So the nice thing about these singular value decompositions is unitary matrices are easy to solve. You just take the transpose. Sigma, this diagonal matrix, how do you invert a diagonal matrix? Yes. That's right. You reciprocate the diagonal elements, which is why when you have zeros on the diagonal, it came from a non-singular matrix. Sorry, a singular matrix, right? But we got rid of all those zeros. So now that the reduced, the trimmed sigma is invertible. So after you've done all that work, you get D equals V, whoops, that's an inverse, U transpose X. So I skipped a bunch of steps in there, but exercise for you. I skipped a step up here. So solving least squares problems, you can solve it like by solving the normal equations. You can also solve it, it's actually a really nice convex problem to solve iteratively. So we can use gradient descent to solve the least squares problem. So here I've posed it as a sum of this thing squared. So gradient descent, what do? You take the gradient of L with respect to D, right? That gives you your gradient, and then you just keep pushing D in the opposite direction. So what we need is a gradient of L with respect to D. One over P, sum over P. So how I got this is not obvious, but it's something that we actually cover in, well, sometimes cover in CS 370. So this thing here is a column vector. So you can rewrite that as 1 over P times H transpose HD minus T target. This totally fits the sort of quadratic derivative of quadratic thing, right? The 2 comes down. That's where that 2 went away. The exponent to the 1 less, so it's a 1 now instead of a 2. And then the thing multiplying your variable, in this case, this gets outside. Anyway, first year calculus, but vector stuff, so it's a little more complicated. So you can update your decoding weights, starting with some random decoding weights by incrementing them in the direction opposite that gradient. which you can rewrite as this, H transpose times epsilon. And I write it this way because just to point out that this is an error signal. So this is a common pattern in neural network learning, is the error times the presynaptic activity. When we're updating a bunch of synapses, it seems like this little rule comes up over and over again. The way you adjust the synapses is if you have some error, it's the error times the presynaptic activity. And that's what you use to update your connection weights. So I think even gradient descent follows this pattern. Okay. So as a man and his son are driving, son's in the passenger seat, and son says, "Dad, what's an alcoholic?" And the dad says, "Oh, okay, well, driving along. All right, see those 4 cars in front of us? Well, an alcoholic would see 8 because they see double." And the son says, "But Dad, there are only 2 cars in front of us." I almost messed up the arithmetic there. Okay. Neural transformations. So the goal here is to see how to use population coding to pass data between populations of neurons. Right. So far, we've only looked at interpreting the activity of one population of neurons and decoding values, encoding values in that population, decoding values from that population to some imaginary readout node, us. But neurons send almost all of the output to other neurons, right? That's what their job is, to send information to other neurons, receive information from neurons, send information to neurons. Okay, so how do we, in this population coding idea, let's say a population is encoding some number, how do we send that value to another population? So suppose we want population B to encode the same value encoded in population A. So let's say we've got some input here, some value X, let's say, and we've got some population A receiving input, then we've got a population B. Should have drawn that lower. And then who knows where that goes? The point is we want B to represent the same value that's being encoded in A. So here's a question. Can we just copy the activities from the first neuron in A to the first neuron in B, from the first neuron or second neuron in A to the second neuron in B, and just do a one-to-one copy of activities? I mean, to some extent you could, but you certainly have no guarantee that A and B have the same number of neurons in the population. So already you're going to run into some problems. All right. And secondly, that may not be the most efficient way to do it. So I'm going to say the answer is no, because A and B might have different numbers of neurons. So let's take a different approach. instead, we encode a value into A. Let's say A has n neurons. Now, in order to copy that value from A to B, we're going to actually decode it and then re-encode it into B. Okay, so we decode using decoding weights, I'll call them D sub A, to get X hat, some approximation of X. And then we re-encode that X into B, and I'll call the encoding weights E sub B. And there'll be a bias as well, which I'll call beta, I guess. Okay, so to copy value to B, we essentially decode it from A, and then re-encode it using B's encoders. So here's a step-by-step. So we encode X into population A. I'm going to use, okay, A. So how do we, how do we encode, I'm going to leave a little space there. Encoding X into population A is X times the encoders for A plus the bias for A. And then the neurons in that population have some activation function. Okay. So now A, little lowercase a, is a vector of neuron activities. Let me draw this over here. So there's this data space. Then there's the neural activities. So what we've done so far, we've taken X in the data space, right? This is the data that we have in our mind as the programmers of this neural machine. It's a number we want to use in our little program. We're going to put that into our computer, so to speak, by encoding it into a vector A. So we've taken the information from the data space to the neural representation space. Now, in order to, so that's great, the population A is encoding that value. But if we want to copy it over to population B, which is going to be down here, we have to come back, decode, and re-encode. Okay, so decode an approximation, X hat, from A. Well, it's A times the decoding weights for A. So that goes over here. All right, then we re-encode that approximation into B. Let's go this way. Encode E sub B, I'll call it. So B is, again, activation function applied to X hat, encoded into B. Okay. Now, that's the way we're thinking about it. In truth, though, we could have actually, in truth, the neurons in an actual brain or whatever, they actually go from a population of A through some set of connections directly to a population B. Okay, so, but we can build that matrix with our encoders and decoders. So let's find this connection here. We'll call it W, directly from one population to another population. So now that X hat is actually from A times the decoders of A times the encoders for B plus beta B. Now this dA, is that visible? If I hear one person say no, then I'll change the color. And I heard one person say no. I can easily change it. Oops. Is that color visible? Better? So the decoding weights times the encoding weights, well, that's basically everything from A to B, except for the bias. But in terms of the connection weights themselves, that takes care of it. So we can multiply those two matrices together to get a full connection weight matrix. Where W is decoders from A times the encoders for B. Then optionally, we can decode from B an X double hat. It's getting kind of ridiculous now. Okay, but even though we've got this sort of philosophy of focusing on the data, encoding and decoding that data, we can still turn it into a full neural network with a connection weight matrices. Yeah?
Where does beta come from? Is that like a bias term?
Bias, yeah. Yeah. The encoders are typically chosen randomly. They don't have to be. There is some intelligence that can go into that, but typically you just choose them randomly, maybe from a particular distribution that suits your needs, but that's part of the art of this population coding stuff. The encoding weights and biases are both part of the encoding, and they're often chosen randomly. The decoders don't have a bias, just weights, and those are computed using least squares. I mean, you could say they have a bias if, I mean, you could always have one neuron that's always on, and every connection coming from it is basically serving the function of a bias, right? So bias is kind of extra. Okay. So the reason we connect populations of neurons is because connections can perform transformations on data. So in this case, I just took the value X stored in A, stored that same value in B. That's not very useful. I already had that. But as I showed you before, once you've encoded a value in a population, you can decode functions of that value. You don't have to just decode X, you can decode X squared or sine of X. Or if you've encoded X and Y in a population, you can encode X times Y or X plus Y squared or some nonlinear function of both of those variables. Okay, so as an example, given a population that's encoding XY, this population A here, we've got our encoders E, A, and biases. We decode it. Let me use red. We decode it to X times Y using decoders. I'll call them DXY. This is a set of decoders that we found by solving a least squares problem where the target was constructed by multiplying X and Y. You might have to go back to the previous lecture to sort of see that again. But we know what the neural activities are, and we know what the output target values we're wanting, we just solve a least squares problem to use the linear combination of those neural activities to reconstruct the output. Okay, then that gets re-encoded in B with some other encoders. And we can decode from that if we want. Again, we don't have to just decode X, Y. What's stored in B, we can decode some nonlinear function of it. So where dxy is the argmin I guess I use capitals to represent batches or whole data sets. It doesn't really matter. Oops, squared. Okay, so that XY thing, that's just a tall vector of values, right? Or, yeah, okay. So I point out that there's this low dimensional bottleneck. We're taking, even though we have a full connection weight matrix W, which is like M by N, it actually comes from the matrix product D times E. And D and E are both actually pretty low rank matrices. So W is a full connection weight matrix, but it comes from low rank product. So for example, if dxy is n by 1, so here we've got n neurons in this first population, m neurons in our second population. Decoding weights dxy, what kind of vector is that? Well, it's got to take a linear combination of n things, boil it down to a single number. So that dxy is just an n vector. The column vector, I'll call that a column vector. So it's n by 1. The encoder is also going to be an m vector, but it's going to be a row vector. EB 1 by M. So this W comes from a matrix product that looks like this. N tall and M wide. So we've seen this sort of thing before. In fact, we saw this kind of thing when we were doing gradient descent weight updates, right? You'd often get these outer products. Okay. So this actually has advantages in terms of how you implement it. So we know that we can represent this connection from population A to population B using a weight matrix, just like a neural network. But if we actually are on a computer, we can take a shortcut. And instead of multiplying, there's a lot of redundancy in here, right? It's n times m elements, but it's actually a rank 1 matrix. A lot of redundancy. You actually only need one column on one row to encode all that. So we can take advantage of that decomposition. So to illustrate this, how many flops does it take to multiply a vector? And this should be lowercase a times w. It doesn't really matter. but it's a vector, a row vector, times this W matrix. N by M. This is an N vector. Well, each column is N flops, right? But there are M columns, so it's N times M flops to do that product. Now, what about A times D times E? So using D and E, the decomfactored version of W. Again, here's our A. Our D is like that. This is an N. This is an N. So when you do that product, that's just a dot product. That just takes N flops. Gives you a number. So total flops over here. We have N for the first stage. Now that number, that scalar, is used to multiply by the encoders, of which there are M values. So that product takes M flops. So the decomposed decode encode strategy takes N plus M flops. It's cheaper. Okay. So finally, in creating these networks, a population has a different set of encoding weights for each element it encodes. So just like I showed before, well, it's the last lecture actually, maybe worth going there. So here's encoding an XY into a vector, into a population. I had two different sets of connection weights, these black ones and these light blue ones, right? Different encoders for each dimension that you are encoding in a population. Or if you want, your encoding vector has two rows in it. Okay. If a population has multiple inputs for the same element, they use the same encoding weights. Okay. So here's a population A that takes a scalar as input. And I'll call those E, V. So we can compute X plus Y by putting X in there and encoding X, and then adding to that set of activities, putting Y in here and encoding Y in there. So we basically get encoding of X and the encoding of Y. Careful. You add together the input currents from both of them to get the activities of the populations. Okay, it's because it's 1D. So this population is only encoding 1D information. You can put multiple values in there, but they'll just be added together essentially. Now, if we want to encode X, Y as a vector in this population, that's when we have to have two sets of encoders. So we'll have one set here, which I'll call E sub 1. Then we need a different set, which I'll call E sub 2. Now that population A can actually encode two different values simultaneously. It seems kind of odd that it can do that, but it works. As long as you have enough neurons, it's possible. I'd like to use the last few minutes to sort of demonstrate some of this to you. Now, I have my own version of this written in Python, stuff like that. But let me show you Nango. Nango is like the NE stands for neural engineering. And Nango is a programming framework for creating population coding networks. So okay. So here I'm importing Nango and NumPy. I created a Nango network. I don't think I'm going to expect you to write Nango stuff for your assignment. So this is more just so you know what's out there. And so with that model, we can create an input. So this node is just like that circle with the X in it that I did on the board or on the whatever. Now A is an ensemble. It's 20 neurons, and it's got one set of encoders. So it's capable of encoding 1D information or a number. And I connect my input to my A, and then I say run. So what's it doing? Let's look. So this is, I can change the input like this. Now if we look at what's going on inside A, these are actually, oops, everything I've shown you about population coding, we've been using sort of generic sigma as an activation function, but Nango is pretty much designed around using spiky, leaky, integrate, and fire neurons. So they're actually, it's encoding this information through the spiking pattern of 20 neurons. So yay, you see a bunch of lines going across there. Who cares? That doesn't prove anything. But we can decode the value that's encoding. So now it just computed the decoding weights, the identity decoding weights. So now as I change the input value, it's decoding the corresponding activity of that population of neurons into a value. You can see it tracks really closely. It's a bit bumpy because, hey, these are 20 spiking neurons. So I can encode 2D information. Let's use 100 neurons now. So now I need double input, and it's going to encode in this population A, which now is 100 neurons. It's two-dimensional. So I can change these independently, and what I'm seeing here is it's decoding each of the two different dimensions. All right, let's create another population B. And neurons, how about 50? One. Now we A0 to B. So now the way I've set it up is that B should encode the X coordinate encoded in A. So this is the Y coordinate. You can see it doesn't really affect what's in B, not much, but this first one does affect it. So B is encoding only the first coordinate from A. I guess I can make that bigger. How about we we want to encode the product of x of the two different things in here in B. I can say function equals lambda x x0 times x1. So I've told it what function I want it to decode. Going from A to B, it's going to decode the 2D population of A into x times y, and then re-encode xy into B. Except there's a bug or an error. What doesn't it like? There. So now the x component of in population A is 0. So B is just receiving 0 times whatever I give it as a y. So quite rightly, the value of B stays at 0. But if I make B, let's say 0.5-ish, and I move x, B is going to encode basically half of what's, so B's got a 0.35, well, it's approximate, it's not exact. You can see how yeah, if I make one go negative, then B goes negative. Anyway, it works, okay? Shut up. All right, so this Nango, you can build very elaborate networks that do all sorts of computations using this idea of population coding. So what I haven't talked about yet is the dynamics. So this is running in a continuous time frame. So on Friday, I'll add that one piece of dynamics, adding basically turning it into a system of differential equations that you can run. Okay. Thank you, everyone. I'll see you on Friday.